When users create in-betweens in an interactive in-betweening product cacophony, they have to trace strokes in the same order. For occluded strokes, they must trace them explicitly. After generating in-between frames with the corresponding stroke, they have to hide the occluded strokes using an interactive tool frame by frame. This is time-consuming and laborious for animators, especially when there are many in-between frames. We present LayerInbetween, a framework for vector stroke correspondence and automatic in-betweening that resolves occlusion. It takes two raster keyframes and the vector starting keyframe as input, and outputs layered vector images for the keyframes with one-to-one correspondences for visible and occluded strokes. Strokes of the same color are matched. Our framework also predicts layer masks to resolve occlusions. After generating a raw in-betweening sequence, we use the layer masks to hide the occluded strokes. This produces the final in-betweening result. Our approach generalized well to various types of line drawings. It also works with multi-keyframe sequences. Our vector stroke-based method facilitates an application of in-betweening editing by modifying the intermediate frame and recomputing the interpolation. This editing method is more convenient than raster-based video generation methods. Our framework first performs automatic layering to produce stroke groups and the corresponding layers. We aim to align strokes across keyframes to improve stroke matching, but in this case, we can see noticeable misalignment. We propose a global local layer transformation module which aligns strokes in a progressive manner. First, we aim to align the layers. We crop patches for the keyframes using windows in a reference layer view for the alignment. A global transformation is predicted and applied to the target window. The cropped target patch aligns better with the reference. Then we aim to align each stroke after the global transformation. For example, for this stroke, we also crop patches using windows in a stroke view. We can see that even though this stroke is occluded in the target frame, the global layer transformation helps indicate its possible position. But this also fails in some cases due to non-uniform deformation within the layer. Here, the endpoint prediction fails. Then we additionally introduce a local layer transformation. A predicted transformation is applied to the target window, and the cropped target patch now aligns better. This improves the endpoint position. After the global local layer transformation, our framework predicts corresponding endpoints and control points. The vector stroke correspondence model can handle visible and disappearing strokes, but there are also appearing strokes without reference vector input. We introduce a bidirectional prediction scheme by manually drawing the missing strokes, and then applying the vector stroke correspondence prediction in a reverse direction. This handles disappearing and appearing strokes in a unified manner. After applying a stroke interpolation algorithm for the corresponding vector strokes, we obtain the raw in-betweening results. We then use the predicted layers to resolve occlusion. Please refer to another video for more results.